Magdalena Hauser has a Bachelor of Science in Management Economics from the University of Innsbruck. Then, interestingly, she studied at the University of Applied Science in Coburg and got the Bachelor of Interior Architecture. I always find it very interesting. Yeah? Then she went to an investment company and worked as a director of operations and as a CEO from 2018 to 2020. In parallel, she was a procurator, in and a co-founder, and now she's CEO of Parity Quantum in Innsbruck since 2020. This brings you also to Wolfgang Lechner, studied computer science at TU Vienna and got a Master of Physics in 25 at the University of Vienna, where he also received in 28 a PhD in Physics. Then he went to the University of Amsterdam, in Amsterdam as a postdoc. He was then a postdoc in Innsbruck, long way around. He worked as a senior scientist at Austrian Academy of Science for 6 years. In parallel, he was assistant professor in Innsbruck, and then he became also together with Magdalena co-CEO of Parity Quantum, and now since a couple of months is still professor of Innsbruck. So this was.
Thank you very much.
Over to you. Thank you.
Thank you very much. So indeed, we have a long tradition of always giving talks together. So we also do it here. And the split this time is that I will start actually with a very technical discussion. So I really want to show you what we are doing in the company. And then Magdalena will give an outline about our successes and our business side. Stefan, the clicker was yours? No, I cannot see it. No. No, it's fine. So I would like to start really with the, going down bare bones, what we are doing in the company. And what we're doing is we developed an architecture for quantum computers which represents the data differently than we usually think about computers. And the story will be that usually we think about if we go from computers to quantum computers, we translate the gates to the quantum gates and the bits to the quantum bits. In our case, we developed an architecture where all the information that we have on our chip is relative information between 2 bits. So this means our qubits, they always represent the relative information between bits, and this allows us to completely simplify architectures and also develop new algorithms, which I hope would also run on the IBM machine. So let me start with optimization problems, and then you will see why we are doing this. Optimization problems are omnipresent, and I would like to give you an example, the graph partitioning. So we have a graph, and we ask what is a partition to put this into 2 subsets of equal size such the number of edges is minimized. If we would like to translate this on a quantum device, for example, using the qubit transformation, the strategy is typically to translate our cost function into the energy of a spin model. And we would do this by introducing spins which sit on the nodes. And then we would have, in this case, a quadratic interaction form. So the first part here says that the sum of the sigmas to the squared should be minimized. This means that the 2 subsets are of the same size. And the second term says that you sum over all edges which are basically between 2 different sets. So this is how we would translate such an optimization problem into a spin model. And now you can already see the problem. The problem is that what you get out is the quadratic terms, so that's fine. This is something we can program. However, they are connected more or less all to all, or arbitrarily connected. And this is a huge difference now to classical computers. There we have registers, now we can store and load information. On quantum computers, these interactions really have to physically be applied, which means you have to make a gate between every qubit that we have on our chip. And this is a huge challenge, and there is, of course, mitigation strategies, how we can do this with swap operations and so on. However, this has a large overhead. And what I would like to show you now is a translation into a different paradigm, namely one where we don't translate the qubits into qubits, but actually the edges of our graph into the qubits. So this means we want to represent our graphs purely with relative information, so that the bits represent the relative information of bits in our logical graph, which is called the parity. And what this then will mean, or what comes out then is that the problem is encoded only in single qubit operations. So this means our programming language is not the gates anymore, but it's single qubit operations. And all interactions, all physical interactions, all gates, becoming independent of the problem. And this allows us to build completely different chips. So it allows us to build chips with global control. We don't have to program the gates anymore. We only have to program individual single bit operations. So I will derive this now. So let's start with the starting point, which is the parity transformation. So we have a graph, nodes and edges. Now the first transformation that we do, we introduce the duals or the parity variables, which are variables which sit now on the edges, and they tell you whether the two spins are pointing in the same direction or in different directions. So it's basically just the product of them, right? So if you encode in -1 and +1, then the product gives you -1 and +1. Now for this talk, I made the logical qubits or logical spins blue and with an arrow, and the physical ones, so the ones that are built in green and with a number, but these are both just bits, right? So this is just for visual to distinction. So now the first thing that we see is if we have now an interaction matrix that looks like this. Now let's say we have a graph which has interactions between every qubit I and j. Now if you do this transformation, you already see the first magic already happening, namely by doing this transformation, which means going to the edges instead of the spins itself, the interaction part becomes a single qubit part. Because an interaction like this one would tell us, for example, that if they're pointing in different directions, it would give you a penalty. If you do this in the new variables, so these are the ones with the head, this is now a property that acts on single qubits, namely the ones that show you the relative orientation of the two qubits. So this means you can already see, okay, we have here this double sum, which goes over a matrix, and on the right side is now a single sum. You have quadratic more elements, so sum over all edges, but it's a single sum and it goes over these new qubits. Now, however, there's not an equation in between, and the reason is that there is a mismatch on numbers of degrees of freedom. So here you have n squared elements, here you have n squared elements. However, here you only have n number of degrees of freedom, while here you have n times n minus 1/2, which I call k here, degrees of freedom. So there's a mismatch on degrees of freedoms, which means you have to introduce k minus n constraints to bring it back into the allowed subspace. So you have to kill k minus n free degrees of freedom. Now what are these constraints? These constraints are conditions on closed loops. So let's take a closed loop, 1, 2, 3, and then have 1, 2, 2, 3, 1, 3. Now let's do our translation table here, or the truth table on this side. So if all logical spins are pointing up, so 1, 1, 1, then this translates to 1, 1, 1 because they're all pointing in the same direction. Now if we have all spins down, this also translates to all spins up because they're all pointing in the same direction. Now let's take this example. So down, down, up. So 1 and 2 are pointing in the same direction, so this is up. 2 and 3 are pointing in different directions, it's down, and 1 and 3 down. So this means 0, 0, 1 translates to 1, 0, 0. And now we can continue this truth table, and maybe at some point we arrive at this example, which we want to translate back. So let's say we have 1 and 2 is pointing up, 1 and 3 is pointing up, and 2 and 3 is pointing down. Now it turns out that there is no solution to that, because you would like to have 1 and 3 pointing in the same direction and 1 and 3, but 2 and 3 different directions. There is no solution for this. Which means, if you write down the whole truth table, what you see is that on the right side, on this side here, there is only configurations or bit strings allowed which have an even number of zeros. So on this side, there cannot be an odd number of spin downs. And intuitively, this is actually easy to see. If you flip one bit, one blue one, you always flip 2 green ones. So it's impossible to reach a configuration which has an odd number. And now, this is actually this rule, so this English sentence on the right side only spin even number of spin downs. And this we can translate into an energy, and we can easily translate this into an energy by, again, not thinking about bits, so 0s and 1, but thinking about -1 and +1 basis, so about spins. Because if you just multiply the 3 and put a minus in front, then you always get an energy penalty if the rule is violated, and no energy penalty if it's not violated. So this means in a physical way, what you do is you go from the bits, so 0s and 1s, you go to -1 and +1, and then you just multiply them. If you stay in the bit basis, it would be modulo sum, of course. And now you can do the same game that we just did for these 3 spins, and you can do it for any other closed loop. So in any closed loop, you always have the same number of edges as you have nodes. And if you do the truth table and look at it, then you will always get the same rule, namely that you can construct a constraint out of this by multiplying the physical qubits with each other. So this brings us now to the actual problem, namely which closed loops do I want to select. Because I have n factorial possibilities, and I only need k minus n out of them. I only need n squared minus n out of them. So I would like to select the minimum number that I need. And then I can say, okay, there's many possibilities. Let's have another challenge and say I would like to select now such closed loops that if I physically realize these physical plaquettes or these units here, that they are locally next to each other on my chip. So I would like to select now closed loops in such a way that I can build a chip out of this where I don't have any non-local interactions anymore. And this is, by the way, something where everybody who worked on this thought that this is not possible, because we have here also all connected problem which has arbitrary long-range interactions. Now we want to translate this into something which has no long-range interactions at all and only near stable interactions. But it turns out that there is one solution, and I would like to show you this solution. So the building block is the following. I first show it once. So you go 1 to the right, 2 left, 3 to the right, 2 back. And now let's do it on this side. So I put here now the physical qubits, so they are the edges. So I start with 2, 3, and I order them now by the difference between these two numbers. So this qubit, or this bit that is sitting here, represents the relative information between bit 2 and bit 3. Now, the next one is 1, 3, which I put here, 1, 4, which I put here, and 2, 4, which I put here. So this is now my first plaquette, or my first constraint. And this is the first interaction that I have to realize. Now, for this example, by the way, I have 6 qubits. I need to construct 10 such constraints. So k minus n is 10 in this example. So next step is I take the pattern that I just had with 1 to the right. So now I say 3, 4, 2, 4, 2, 5, 3, 5. And 2, 4 is actually already there. So I can recycle this and put my next constraint next to it. And so on. So I go once through the system, which gives me 3 constraints. Now the next building block is I take the same pattern, but now I stretch it by 1. So now the elements, so I go 2 to the right, 3 back, 4 to the right, 3 back. So now the first element is 2, 4, 1, 4, 1, 5, and 2, 5. And if I look now at the elements that I need here, then I see that 3 of them are already there. So 1, 4, 2, 4, and 2, 5, they are the upper corner of these 2 squares, which means I only have to put the 1, 5 here and have another one. So I can go again through the system, stretch it by 1, go through the system, and so on, and so I get this pyramid shape. And now I have constructed 6 constraints. As I said, I need in total 10. And these 10 are actually hidden here. So these are the triangles down there. So this was the example that we looked at. Then there's 1, 2, 3, 4. So this means I have now exactly the correct number of constraints that I need. And just to summarize what we did, and one detail here, by the way, so this is what we just constructed. And in the original paper, we put here bits which are fixed to +1. Because if we do this, then all the constraints are 4-body, or products of 4. Otherwise, we would have here products of 3, and the rest would be products of 4. So what we have done now is we've translated an arbitrary graph into a new graph where the nodes represent the edges of the original graph, and the edges, so to say, are hyper edges. They are always products of 4 qubits. But the trick is, or the really interesting thing here is now that there's no long-range interaction. Every interaction is only between nearest neighbors. And this is, of course, something very convenient then for compiling quantum algorithms, and I will show them how we do the compilation. Now, there's a few, so this was 2015, by the way. So in the meantime, there's 60 people working full-time on this architecture, and we developed compilers and so on. And I would just like to show a few ideas here. The first thing is the compilation itself. So in the derivation that we just saw, we would take an arbitrary graph, and we would always get out this triangle. So it's rotated here, but it's the same triangle. However, not all graphs are all-to-all. Sometimes you may have less than all-to-all graphs. So for example, here 6 is missing, 2, 5 is missing, and so on. Which means if you would just do the naive thing that we just saw, which is often called the LHZ. So if you would do just this first transformation, you would have qubits, this one, the bit 2, 5, for example, which would have a local field 0. But it would still be there. You would still need to build it on the chip. And however, it's a useless qubit. No, it has no local field, no information, so you would like to get rid of it. Which means what you would like to actually do is you would like to find another hypergraph, which is again planar, and which only has as many qubits as it has nodes. And it turns out that this is always possible. However, it's a very challenging problem. It's a challenging graph problem. So you basically have to take all cycles of length 3 and 4 and put them together in such a way that they all share some common nodes, such that you can make them in a compact way. This is what our compiler does, but it's in principle always possible. Another interesting thing about this encoding strategy is that you cannot just encode 2-body problems, but you can encode arbitrarily higher order terms. So you don't have to do a qubit transformation, you can do arbitrary higher order terms. And the way this works is by generalizing the definition of our constraints. So our original definition was that it has to be a closed cycle. And the reason it is a closed cycle is the following. If you look at these new spins that we have, they are always the product of two spins, like 2, 6, 2, 3, 5, 6, and then 3, 5. This would be a closed cycle. And what you actually do here is, in the end, you multiply them, which means if you multiply them, you see that every index occurs twice. And so this means for a graph, the closed cycles are the only possible constraints. However, if you have now a hypergraph, which means you have also products of 3 in it, so not just pairs, but products of 3, then you can take this generalized definition of a constraint, and you can just look at all the indices that we have, and if all the indices occur with an even number, then this is a valid constraint. And this allows you now to also map higher order terms. So for example, this plaquette here, which has two body terms and two free body terms, is a valid constraint, and you can use it in your construction. And so this means that typically, if you think about these optimization problems, we first have to go via Cubo transformation and then somehow encode this on our chip. While in our case, we can directly compile this to a quantum chip, and in this example, we only have 6 qubits, while if we would go via Cubo transformation, we have up to 28. So this is just a gallery, so it shows how different graphs translate to these parity graphs. So I always like to show this because it somehow shows this fundamental nature of this transformation. So if you look at this one, for example, if the original graph has some pattern, then the new graph also has some pattern, and you can somehow see the symmetry in these things. But what you can always see is the compiled graph is always a square lattice with nearest neighbor interactions. Yeah, maybe also just very short constraints. So we are replacing Cubo here, no? So we replaced already the quadratic requirement. We also replaced the unconstrained requirement. So usually if you have a constraint in your problem, then this gives you an additional overhead because you have to include it in the form of a Lagrangian, which means you get additional terms in. However, if you think about it from an information point of view, a constraint should actually make the problem simpler, right? Because you have less degrees of freedom. And in the parity transformation, you can actually make use of this. And the way this works is as follows. Imagine you have the graph that we've just seen, but now we have an additional constraint that 2 and 3 have to point in the same direction, which means the product of 2 and 3 will always be +1. And this actually allows you to compile the graph in such a way that you can remove a qubit. And this is very convenient because it allows you to compile really hard problems onto a very simple chip. So this is an artificial problem that we generated, so it has a lot of terms, up to 5 order terms, and it has a list of constraints, and you can still map it onto a square lattice. And if you would do this, so to say, in the standard way by translating to pair interactions and adding the constraints, you need more than 700 qubits, while here you need only 50. Also, because we had the question about neural networks, one very interesting thing about this architecture is that the bipartite graph has a very special form in the parity mapping. In the parity mapping, the bipartite graph becomes a rectangle. So one way to imagine this is, in a bipartite graph, now you have 2 layers, let's call them visible and hidden. And now remember, in the parity mapping, every node represents the relative information, which means in a neural network or in a bipartite graph, you only have relative information between 2 neighboring layers, but never in the same layer. And this means that instead of a triangle, you get a square now, because you can imagine that, for example, this qubit here, or let's take this one, this qubit would represent the relative information between hidden qubit 1 and visible 5. And now you can draw them all in a line. Or you can say this is always visible 5 with hidden 1, hidden 2, hidden 3, and so on. And in the horizontal, it goes like this. It's always hidden 1 with vertical 5, vertical 3, and so on. And this means if you have now a bipartite of 5 and 3, you get a rectangle of 5 times 3. And now if you make a deep neural network, it's like rectangles which are attached to each other like this. And this actually allows one to do really a very nice and new form of quantum machine learning. Okay, and before I switch to the business one, I just want to say that what I talked so far is about optimization problems. However, the whole concept is sort of say independent of what you do actually in the end. So if you represent any quantum circuit in this parity language, you can do a universal error-corrected quantum computing again with the advantage that you don't have to do any long-range interactions. And long-range interactions on logical qubits is something that's really very painful and has a lot of overhead. And we actually developed, based on our parity mapping, a code which actually allows you to do logical qubits between arbitrary interactions. And Frank, if you invite us next year to this venue again, I will talk about this. Okay, and now we will switch to the business part. Which starts?
Hm? 20. Du darfst auch schneller reden, ne? Aber 20.
Can you hear me?
Yes.
Okay. So thanks. What does Parity actually do? So we call ourselves a quantum architecture company. So it presents a little bit like ARM for the classical computing. This is what we try to do for quantum computing. And so we don't build actually quantum computers ourselves, as you might have noticed from the talk before, but we work together with hardware developers. And in quantum computing, it's not quite clear if superconducting devices like IBM are the ones winning the race, or if it's neutral atoms or ion traps or photonic quantum computers. So we try to build the architecture with as many hardware developers as we can. And one interesting project that we have, which also deals with QA/OA, is with Quanta, which is now Inflection, and they build quantum computers based on neutral atoms. And what we did was, in the darker honest code, we tried to develop a scalable code as a quantum computer based on our architecture, which demonstrated potential quantum advantage. But this was back in 2020. Another one that we are quite proud of is the NEC machine, which is an annealing device, so no digital quantum computer, but annealing. And they are building this in Japan, and they are building this only with our architecture. And they made this available to the cloud in last year in summer. Only 8 qubits, but they tried to advance this, of course. And maybe the biggest news for us was that Chancellor Olaf Scholz, so he's very proud of pushing the button there, but this is how you have to do it for politicians. But he opens the quantum computer that we built in Hamburg with Electron, which is an ion trap hardware developer, and NXP, which some of you might know, which is a semiconductor company based in Europe. And yeah, so the DLR was given quite a lot of money to purchase quantum computers. So they spent $208 million for 5 contracts to build ion trap-based quantum computers, and we won 2 of these contracts together with our consortium. So this is only a quantum demonstrator. It only has 10 qubits, so it's really only for research. But the next stage should have more modular, let's say, outlook to a scalable quantum computer. What else? So I'm going to bore you with some market slides. I borrowed this from McKinsey because it is quite good. So we have two types of investments in the quantum computing market. It's private and public. And we do need this because the market is still very tiny. So about 600 million last year. So this is not where so many companies, so 376 companies can survive from this. And this is not including the big ones. And so far we had 8.5 billion invested in quantum computing, which is over the last 10 years, not so much. And most of it, of course, in the US. So even though Europe has 24% of all the companies that we see here, only 5% of the funding goes to Europe. So we always manage to have fantastic research, but then we lack the commercialization. And just to give so where are we in quantum computing? It's always asked. So yeah, so AI had some quantum winters, some AI winters. Do we have the same in quantum? And in terms of investment, we are now where AI was a decade ago. So comparing these numbers, I hope we don't have so many winters as AI has and survive a little bit faster. But this all pays on what governments are currently investing. So we have 42 billion invested by governments or pledged to invest. And well, the government that stands out here, I don't know if you can see it, is China. So this would be much bigger if China was there, but it's China. And then we have Germany.
What is blue versus white?
That's announced before 2023, and blue is announced in 2023. So yeah, in the US, we have the venture capitalists that are driving the development. In China, we have the government driving the development, but in Europe, we have to find our middle ground. And there might be some hedgehogs there.
Excuse me, did I understand correctly here that Germany invests more than the United States?
Yes.
Sure.
It does. It does, but in the US, you do have a venture capital market that works, right? So it makes up quite a bit, and you have the tech giants like IBM, they can phase out of their own pocket.
Well, but I mean, I still think it's quite striking that the US government is investing less than the federal.
Thanks to Merkel, she was a physicist. Thanks to Merkel, she was a physicist.
But they have to do it continually.
They will, Magdalena, we will check.
So what do we actually do with this point here? So if everything holds true that Stefan presented in Q&A, quantum utility will be the next step towards quantum advantage, hopefully, where we can show that quantum computers do have an advantage in solving problems for the material science industry, for life science, for finance and mobility. And if we think that McKinsey is right, and hopefully once they are, we have a potential economic value of 2 trillion once we have technological maturity for quantum computing. And we do want to participate in this. So a quick overview of what Parity is doing. So we're over 60 people working full-time on this. It's not only a company, but also a research group. We work on that's on the side of his 30 hours a day work. We have team members from all around the world, so they are really coming back to Europe to work on this. We've been founded in 2020. We're a spin-off from the University of Innsbruck and the Austrian Academy of Sciences. We have offices in Austria, Germany, and also UK. We have now investors. This is only one of them. So Hauser, if you notice, one of the helpers to spin our arm. And we recently closed the funding round and are now running what of the beginning, which is quite nice. Helps us to go further. So thank you very much.
Any questions?
On the compilation, can you compile to other architectures than database?
Yes, yeah, so ParityQC is of course also a possibility. And the square lattice has kind of a special form for us because it is the most compact form. Now, the heavy hex is also possible. Interesting maybe I'll just say the story. There is one very interesting thing. So the answer is yes. The answer is yes.
I guess you pay some price when
Exactly. Yes, you have less connectivity, so it's you need more qubits to actually do it. But I would like to show one thing, because I talked so much about graphs. I want to show one more thing here. So remember, the number of constraints that we need was k minus n. And there's a +1. This is a subtlety which comes from the fact that the original problem can have a global spin flip symmetry, while this has never a spin flip symmetry because it is free body trips. So there's a +1 here. So k minus n plus 1 is the number of constraints. Now the constraints are the faces of this graph. And now the super remarkable thing about this, so this we derived, remember we derived from the number of degrees of freedom. There was nothing about geometry. This was degrees of freedom counting. We said we have k degrees of freedom, we have n degrees of freedom, so we have the kilocalories. Now, k minus n plus 1 equals the number of faces is actually the Euler formula for planar graphs, which again has nothing to do with degrees of freedom, but it's a purely geometrical thing. And it's the same formula, and I really don't know what this is the case.
You don't know?
No, I have no idea. So this is, it comes from completely different sides, no? But it means that every graph can be compiled to a planar graph, which is very fortunate. But it's a very deep connection, which I don't know where it comes from. Maybe there's some connection. And so Euler wrote here 2 because he counted the outside as another face.
More questions? Okay.
If you have more or anything,
You speak up louder?
We can also not make use of more, interestingly, so because it gives you redundant constraints. So the square, the square lattice in 2D has some special meaning here. I think it's more or less the optimum. So for example, a triangular lattice you cannot use because if you have a triangular lattice, you always have something like this. You have a triangle here and a triangle here. And if you have a triangle here, then this qubit must be identical to this one because they're the same product. And that's why you cannot use only triangles for it. So the square lattice has some special meaning.
Theoretical question. If you apply the parity transformation twice, then you go back to the identity. Is that correct?
If you apply it twice. So this will become the qubits, right?
Mm-hmm.
I think you don't get back, you make it worse again, right? Because, let me think. I think to go back, you have to use it on these edges. So if you translate these edges again, then you go back to the qubits. But I think the actual translation would be that the 4-body terms become.
Exactly. You could translate
I mean, did you do it in your heads? I never thought about it.
I guess the constraints would again convert back, so that the constraints become again single qubit operators.
You write it bigger.
I never thought about this. That could be interesting.
Is there one more question? No, then thank you very much, Magdalena. The next speaker for the keynote is Michael.
Break.
Coffee break. Okay, it's a break. Okay, okay.
25 minutes coffee break.
5 minutes? 25 minutes coffee break. Okay. 5 minutes.
Fine.
Absolutely.